Welcome to the course on electromagnetic fields and waves. These last lecture's subjects are potential functions, electromagnetic boundary conditions, wave equation, and electromagnetic waves. Let's remember the Maxwell's equations. This table summarizes both the differential and integral form of the four Maxwell's equations, which have names as Faraday's law, Ampere's circuital law, Gauss's law, and no isolated magnetic charge. Together with the Maxwell's equations, when we use continuity equation and Lorentz force equation, we complete the foundation of electromagnetics. Remember that previously, using a postulate of divergence of B is equal to 0, we have defined a vector potential of the form of B is equal to curl of A, where A is vector magnetic potential. From the Faraday's law, we have a relation of curl of E is equal to minus del B over del T. And if we insert the definition of B into this equation, we can rewrite it in the following form, which reads finally as curl of E plus del A over del T is equal to 0. And similar to the case in electrostatics, if a curl of E is equal to 0, then E can be written as a minus gradient of a scalar function V. Then we can rewrite this as E plus del A over del T is equal to minus gradient V. That is, the electric field is equal to minus gradient of potential, scalar potential V, minus del A over del T, where A is vector potential. So this is the general relation of electric field as a function of potential functions. The potential function V is due to a charge distribution, while the potential function A, or its derivative with respect to time, gives you time-varying change of the vector potential. That is, it's due to time-varying magnetic field. If we use the relations of H is equal to B over mu and D is equal to epsilon E, the Ampere's circuital law becomes of this form. Furthermore, when we use the vector identity of curl of B is equal to curl of A, which is equal to this relation, we can write down the following equation. This equation from the previous slide has this final form. When you read it, del square E A minus mu epsilon del square A over del T square is equal to minus mu J plus gradient divergence of A plus mu epsilon del V over del T. As in the case of electrostatics, we make a special choice here. That is, we choose a condition that this quantity in the parentheses, that is divergence of A plus mu epsilon del V over del T, is equal to 0. This assumption has a special name which is called as Lorentz condition or Lorentz gauge for potential. Therefore, the equation for the magnetic potential A takes the following form: del square A minus mu epsilon del square A over del T square is equal to minus mu J. This is the so-called non-homogeneous wave equation for the vector potential using Lorentz gauge. the non-homogeneous wave equation for the vector potential is given with this relation. It has a form of a wave equation. That is, the solutions of this equation represent waves traveling with a speed of 1 over square root mu epsilon. Since the electric field is equal to minus gradient V minus del A over del T, divergence of E can be written in this form, and we can further rewrite it to become of this form. Remember the Lorentz gauge condition given by this relation and the fact that divergence of V is equal to rho over epsilon. Using this, we can write down the following relation, which further reduces to del square V minus mu epsilon del square V over del T square is equal to minus rho over epsilon. This is the non-homogeneous wave equation for the scalar potential. Now let's shortly discuss the electromagnetic boundary conditions. Consider this picture where we have a boundary between medium 1 and medium 2 and an electromagnetic field is coming from medium 1 and enters medium 2. We define a closed contour A, B, C, D of the following form with V and height h. In general, if we let h to go to 0 such that the surface integrals for del D over del T and del D over del T vanish, from Maxwell's equations we can end up with the following two boundary conditions. The first boundary condition is for the tangential components of E and H. We can prove that the tangential components of the electric field are continuous and that for the H field are discontinuous by this amount given in this equation. The second boundary condition is for the normal components of E and H. In this case, the normal components for the D field are discontinuous by an amount given with this equation, while the B field, the normal components of the B field, are continuous. Let's consider again the interface between a dielectric and a perfect conductor. For a perfect conductor, we have the following four properties. The first property is that no E and H is present inside an ideal conductor. Second property is that only surface charges and surface currents are allowed. Third, the electric field is normal to the surface. If positive charges, then outwards from the conductor. If we have negative charges, then into the conductor. And the final property is that H is tangential to the interface. Let's consider the non-homogeneous wave equation for scalar potential V and vector potential A, which are given by these two relations. The solutions of these equations are called retarded vector potential A r of t and retarded scalar potential V r of t. The details of these potentials are out of scope of this lecture, so please refer to any other electromagnetic book for the details. Consider the source-free wave equations. The source-free Maxwell equations are given in this bracket. We have four equations where curl of E, curl of H, divergence of E and H are defined. If we use the following vector identity of curl of E is equal to this relation, and further substitute the corresponding properties of the Maxwell's equations into these, we obtain the following relation, which reads as del square E minus mu epsilon del square E over del T square is equal to 0. That is, we end up with a wave equation. Maxwell's equations are linear differential equations that hold for electromagnetic quantities with arbitrary time dependence. Typically, the actual type of time function depends on the source function, ρ and j. Using the sinusoidal time functions, any periodic time function can be expanded into Fourier series. Using the principle of superposition of sinusoidal harmonics, we can obtain the total fields. That's why in electromagnetic fields we use time harmonics. The phasor notation for time harmonic fields, we take the cosine function as a reference. Then all the derived results will refer to the cosine function. For example, I of t is equal to amplitude I times cosine omega t plus phi, where omega is the angular velocity and phi represents the phase. The derivative of e to the j omega t is equal to this, j omega times e to j omega t, or we can represent del over del t with j omega. Using similar approaches, the Maxwell's equations in phasor expression can be written in the following form. The homogeneous wave equations for E and H in source-free regions, Maxwell's equations with source-free in phasor expression are these, and the homogeneous vector Helmholtz equations become these. In Cartesian coordinates, their solution can be decomposed into three one-dimensional homogeneous scalar wave equations. In a source-free, non-conducting, simple medium, homogeneous vector wave equations in E and H are of this form. Here U represents c, or the speed of light, which is approximately equal to 3 times 10 to the 8 meters per second. The solutions of these wave equations is of the general form of c times e to the minus j beta z and c2 times e to the j beta z. In Cartesian coordinates, for example, when we consider the wave equation, this is the equation that we end up with, and specifically for a plane wave, we have additionally these two relations, and Ex component is a function of z only. The solution to the wave equation is a sum of counter-propagating waves in plus and minus z direction, with amplitudes of E0 plus and E0 minus. For the traveling waves, we use time harmonic wave equations, and using a constant phase argument, we define phase velocity to be equal to this term, and we define two other important parameters. The first one is the wave number, which is equal to 2 pi over lambda, and the wavelength is equal to 2 pi over k. Let's consider the transverse electromagnetic waves. Transverse means that the directions of amplitude vibration of electric and magnetic fields is perpendicular to the direction of propagation. We can also talk of another types of waves, for example longitudinal waves, in which the direction of amplitude vibration is parallel to the direction of propagation. Example of these are acoustic waves. For the plane waves in electromagnetics, we define polarization. If light in the form of a plane wave in space is said to be linearly polarized. If light is composed of two plane waves of equal amplitude by differing in phase by 90 degrees, then the light is said to be circularly polarized. If two plane waves of differing amplitudes are related in phase by 90 degrees, or in the relative phase is other than 90 degrees, then the light is said to be elliptically polarized. This is the end of our final lecture on electromagnetic fields and waves. Good luck!